Hello students, in this video let us discuss about the bond angles of inorganic molecules. Okay, so the factors affecting the bond angle are the first one is the hybridization. So here in case of the sp hybridization, that bond angle is 180 degrees. Okay, and next in case of the sp2, it's a planar, so 120 degrees. In case of the sp3 tetrahedral, the 109 degrees 28 minutes. So based on the number of hybrid orbitals, here 2 hybrid orbitals only, just here 180 degrees, 3 hybrid orbitals here, 4 hybrid orbitals. So here in this case we can discuss like this here, BeCl2. Okay, that has a sp hybridization, so bond angle is 180 degrees. Now here BeCl3. Okay, and next CCl4 or CH4 tetrahedral, so bond angle is 109 degrees 28 minutes. Okay, so of course here for CF3 molecule also bond angle is CF4 molecule also bond angle is 110 degrees 28 minutes. So here for sp hybridization higher the bond angle, for sp3 hybridization lesser the bond angle. And next here lone pair of electrons. Okay, lone pair of electrons, how affect the bond angle. So first suppose CH4, all are the bonding atoms. Okay, so no lone pair of electrons present on this central atom. So the bond angle is 109 degrees 28 minutes. Now here in this case, here one lone pair. Of course you know that this one has a pyramidal shape. So in this case here, this is the bond pair, this is the bond pair. So bonding electrons are attracted by the two atoms, but here non-bonding electrons only present on that central atom. So this non-bonding electrons occupy more space. So non-bonding electrons have more repulsions with this bond pair. So here more repulsions, these two are separated each other to reduce the lone pair bond pair repulsions. So then here bond pair are coming closer. That's why here bond angle decreases than the 109 degrees. Now here in water molecule, there are two lone pair of electrons. So in this case, higher the lone pair repulsions, because this one occupy more space, this one occupy more space. So as a result of the higher lone pair repulsions here, this bond pair repulsions are less. So these two are coming closer. So here bond angle decreases to the 104 degrees nearly. Here bond angle decreases to the 107 degrees. Now we are coming to the XeF2 molecule. Here in XeF2 molecule, here there are the three lone pair of electrons. Here fluorine, here fluorine. Okay, so actually here this one is a linear actually. XeF2 has a linear shape, so here the bond angle is 180 degrees. Okay, so in this case three lone pairs are in the plane actually. Okay. So actually here that these two bonds are present in a single line. So bond angle is 180 degrees. So then here bond angle, so higher for the XeF2, and next CH4, NH3 and H2. That's it. So next electronegativity. Okay, electronegativity of so either bonding atoms or that's it. So here electronegativity of the bonding atoms or central atom can affect the bond angle. So in this case H2O molecule, its bonding electrons are very close to the central atom oxygen. Here bonding electrons are away from the central atom oxygen, because here fluorine is a more alkylate. So bonding electrons are very close to the oxygen. So in this case, more bond pair repulsion, then here H2 has a higher bond angle. Next in this case, so here higher the electronegativity of the bonding atoms here, lesser the bond angle. So here in this case here, the central atom, that bonding atom electronegativity decreases, bond angle increases. So here in this case, OBr2 has a higher bond angle next to OCl2 and OF2. Okay, here in this case also NH3 and NF3, here this bonding atom hydrogen electronegativity less. So that's why here NH3 has a higher bond angle. Okay, that's it. That means here in this case bonding electrons are very close to the fluorine. Here bonding electrons are very close to the nitrogen. More bond pair repulsions like this H2O and F2O. And next here the electronegativity of the central atom is different. So here in this case oxygen, hydrogen, this is a hydrogen. So actually here bonding electrons are very close to the central atom oxygen. So in this case tellurium and hydrogen, this hydrogen, bonding electrons are not close to the central atom. So in this case more bond pair repulsions. So here in this case the electronegativity of the central atom decreases, the bond angle decreases. Okay. So in this case electronegativity of the bonding atom decreases, bond angle increases. It is a difference of the bonding atoms electronegativity. Here in this case difference of the electronegativity of the central atom. That's it. And similarly here you can see in this case also NH3, PH3, ASH3. Okay, nitrogen is a more electronegative, so bonding electrons are close to the nitrogen. So in this case from nitrogen to stibbium electronegativity decreases. So here the closeness of the bonding electrons towards central atom decreases from nitrogen to stibbium. And one more interesting point, all these molecules nearly the bond angle is 94 to 89 degrees between that. Here in this case bond angle you know that 107 degrees. Okay, here also same bond angle nearly 94 to 89 degrees. Okay, so why? Because here this molecule is formed by the hybridization. This molecule is formed by the hybridization, nothing but sp3 hybridization. And here these molecules are not formed by the sp3 hybridization. Those are formed by the overlapping of the pure atomic orbitals. Okay, so that is explained by the Drago's actually. There is nothing but Drago's rule. So now here when these atoms are formed by the overlapping of the pure atomic orbital, so you know that on the phosphorus or sulfur, here s orbital, these p orbitals are perpendicular each other. That's why nearly bond angle 90 degrees. Okay, that is a Drago's rule. And next here, let us discuss some more examples. Yeah, size of the bonding atoms in this case. So here in this one, here hydrogen is smaller in size. This is a methyl group larger in size. That's why more repulsions. Here bond angle increases to the 111 degrees. You know that bond angle nearly 104 degrees. So dimethyl ether has a higher bond angle than the water molecule. So here also same case. Here the fluorine smaller atom. Here bromine is a larger atom. So this bond angle particularly increases. That means here the halogen carbon halogen bond angle increases. And here a very interesting point. Here first suppose here bond angle is x, here bond angle is y, here bond angle is z, x less than y less than z. First suppose here bond angle is p, here bond angle is q, here bond angle is r. So whenever the bromine larger in size, so here bond angle increases, then this bond angle slightly decreases. That's why here in this case p greater than q greater than r. Okay, that's it. Next, this one also same with increasing size of the bonding atoms here, electronegativity increases, we can say that. And next here, this one also another example you can see. Here this bond angle is x, this bond angle is y, this bond angle is z. So here in this case x less than y less than z, because bonding atoms size increases, so bond angle increases. So then here in this case here bond angle p, here bond angle q, here bond angle r, here p greater than q greater than r. Okay, so because here these are the larger atoms, so there is a more separation between these two atoms than here. These two are little bit come closer. That's why here less bond angle when compared with this one. Okay, next here, effect of the double bond. So actually you know that here this double bond occupy more space. There are two covalent bonds. Here it is only one covalent bond. So here more repulsions, here less repulsions. Now here in this case, first suppose it is a theta 1, it is a theta 2. So here theta 2 greater than the theta 1. Because there more double bond occupying more space, that means here more bond pair repulsions. That's why this angle increases, this angle slightly decreases. Okay. And next in this case also you can take here between two single bonds theta 1, here single bond double bond theta 2, here double bond theta 3. So here in this case theta 3 greater than theta 2 greater than theta 1. Of course here sulfur sp3 hybridization tetrahedral shape. Okay, but here in this case interestingly we can see one molecule, one ion, that is nothing but CO3 minus 2. So in case of the CO3 minus 2, here carbon, oxygen, here double bond O, here double bond O, here bond angle X, here bond angle Y, here bond angle Z. Here in this case interestingly CO3 minus 2, okay, minus 1, here minus 1. In this case interestingly all bond angles are equal because it is a actually the real structure for this one is a hybrid. Okay, the carbonate CO3 minus 2 exhibit the resonance. As a result here partial negative charge, here partial negative charge, partial negative charge. So this negative charge is delocalized because of the pi electrons. So as a result all carbon oxygen bonds have equal nature. So here all these bond angles are same. Okay. Of course here we can say similarly for a sulfate ion also. S double bond O, here double bond O. O minus, here O minus. In this case for sulfate ion all bonds are the same nature like this one. Partial negative, partial negative, partial negative, partial negative. So here in this case partial bond character. So all bond angles in this case equal. It is exactly tetrahedral shape. Here exactly bond angle 107 degrees 109 degrees 28 minutes. Okay, that's it. And next so you can see the so what is the bond angle order of these molecules? Okay, so BF3, BCl3, BBr3. Here electronegativity of the bonding atoms different. So here give your answer in a comment box. Okay. Yeah, finally there are the two interesting examples. So in this case NH3, NH2 minus, NH4 plus. Okay, so you know that the NH3 pyramidal that bond angle nearly 107 degrees. So here NH2 minus that has a the hybridization of this one. N minus means here 1, 2, 3, 4, 5, here 6. N minus means here we should add one more electron. So here there are the two hydrogens. So in next here two lone pairs and two sigma bond, that equals to 4. 4 means here sp3 hybridization. sp3 hybridization with two lone pairs that has a V shape. Okay, there are the two lone pairs. Here there is a more lone pair effect in this case. That's why here this one has a bond angle less than 107 degrees. But here NH4 plus ammonium ion sp3 tetrahedral, so bond angle 109 degrees 28 minutes. So here in this case this NH4 plus has a higher bond angle, next NH3 and least NH2 minus. Okay, so of course here also for this one nearly 104 degrees, here 109 degrees 28 minutes. That's it. Okay, so next finally NO2 plus, NO2, NO2 minus, NO3 minus. So NO2 plus is linear, that means here sp hybridization, there are the two sigma bonds. So here bond angle is 180 degrees exactly we can say. Next here NO2 is an odd electron molecule. So here nitrogen and oxygen there is a double bond, but here in this case this nitrogen 2 electrons form a dative bond with the oxygen atom. So next here remaining 1 electrons because here nitrogen has a 5 valence shell electrons. So there is a 1 electron system. Now in case of the NO2 minus, here N nitrogen 2 bonds with oxygen, 1 bond with the O minus. So here in this case remaining 2 electrons. Okay. Next here NO3 minus is the structure of this one. So here in this case NO3 minus exhibit the resonance. So here this is the resonance hybrid actually. So in this case all bond angles are equal. That means your sp2 here the planar molecule, so the bond angle is 120 degrees. Okay, so here in this case 120 degrees. Now here coming to this one, these two have V-shaped molecules. So V-shaped molecule means here the bond angle less than the 120 degrees. Which one has the least bond angle? So in this case there are the 2 electrons. 2 electrons means here occupy more space. So that means here with this bonding electrons repel with this 2 electron, that means lone pair. Okay, So that's why here more repulsions, this bond angle decreases. And next here in this case, you can see here there is just one single electron. Okay, there is a one electron. So in this case, single electron, this bond pair repulsions are less. But in this case, two electron bond pair repulsions are more. So that's why your bond angle decreases. This can come closer. So here, that's why here in this case, NO2 has a higher bond angle than the NO2 minus. So finally, the bond angles are also the NO2 plus, next NO3 minus, and next NO2, and next NO2 minus. Because here in this case, two electrons occupy more space, causes more repulsions, then these two bonds come closer. That's why least bond angle. But here single electron occupy very less space. So when compared with this one, there is a less bond pair repulsions in this case. Okay, that's it. So there is the bond angles, factors affecting the bond angles, and in next video I will discuss the what is the back bonding effect on the bond angles. Okay, that is a more interesting, very useful for the J advanced examination. Okay, thank you.